Welcome to the Random Interaction Seminar of the Department of Theoretical Physics in TIFR Colaba, Mumbai. We have with us our speaker today, Shubhayu Chatterjee from University of California, Berkeley. Uh, and Shubhayu had done his PhD with Subir Sachdev at Harvard, and then he moved to Berkeley, where he has been working on magic angle graphene. And today he will tell us about superconductivity from skyrmion condensation in magic angle graphene. And Shubhayu has been very kind to be up late and give us this seminar. So welcome, and over to Shubhayu.
Right. So thanks, Rajdeep, and thanks everyone for being here. In an alternate universe, I would actually be there at TIFR while giving this seminar and would also get to enjoy the nice ocean view. But sadly, because of COVID, that's not happening. But anyway, I'm still glad to be able to present some of my recent work, which I am excited about to all of you. Okay, so I'm going to talk about superconductivity and an all-electronic mechanism of superconductivity via skyrmion condensation. And while this work is motivated mostly by physics in magic angle graphene, it is not specific to magic angle graphene. And indeed, I will show some numerical evidence of the basic or minimal ingredients for such model. But I will also argue that this is relevant to magic angle graphene. So since magic angle, okay, so this work has been done in collaboration with a lot of fine physicists. So there is Eslam and Ashwin at Harvard, then Matteo at Stanford, and then there is Nick and Mike at UC Berkeley. And parts of it in different contexts have appeared in these papers. Okay, so since this work is mostly motivated by magic angle graphene and we think it has some relevance to superconductivity there, I will start by giving a very brief introduction to magic angle graphene, although this audience probably doesn't need much of an introduction. What is magic angle graphene? Basically, you take two layers of graphene, monolayer graphene, and then you twist them with a relative twist angle of theta. And it was found in this by now famous work by Bitstritzer and MacDonald that if you make the twist angle close to a magic angle, which is approximately 1.1 degrees, then you get nearly flat bands. So why do you get such flat bands? Well, understanding it is kind of non-trivial, but basically there is some tunneling in between the layers that induces a moire potential at a much larger length scale. And very roughly speaking, this moire potential can be thought of like a magnetic field which gives rise to a flat band. But we can do better than this rough explanation and just try to solve for the free electron band structure. So just take the Hamiltonian of the two monolayers and add the tunneling, which induces the moire potential. And then, of course, the original bands of the monolayers will get reconstructed. And in particular, at the magic angle in the Mini-Brillouin zone, we find that numerically there are 8 active low energy bands, 2 per layer, 2 for valley, and 2 for spin. So it is good to remember here that layer is no longer a good quantum number because the electrons in different layers are hybridized by the tunneling term, but valley and spin are still good quantum numbers. And much like monolayer graphene, where there is inversion and time reversal that protects Dirac cones, even in this case of twisted bilayer graphene, there is C2 and T, which protects Dirac cones within the Mini-Brillouin zone at K plus and K minus points of the Mini-Brillouin zone. And so this figure on the left shows the band structure in one of the valleys. These are the two flat bands. As you can see, they have fairly small bandwidth, around 5 to 10 MeV, and they are separated from the other quote unquote remote bands by a fairly large band gap. And the other bands can be obtained from these by time reversal, which will give the bands in the other valley. And of course, they're also SU2 degenerate. So there is another spin component. All right, so why is this exciting? Or so part of the reason these magic angle graphene has garnered so much attention over the last couple of years is because one of this observation of correlated insulators. So as I was discussing, there are these flat bands within the Moire-Brillouin zone or mini-Brillouin zone, and there are 8 of them. Now I will count them from charge neutrality. So I will refer to the filling as going from -4 to +4, with 0 being charge neutrality. +4 means all the flat bands are filled, -4 means all of them are empty. So as expected, when Pablo's group did these conductivity measurements, they found that there are insulators at filling of +4 and -4 of these bands, which essentially amounts to all of these flat bands being full or empty. But in addition, they also found other insulating states at filling -2 and +2. And these could not be simply explained by a free electron picture, as at these fillings within the free electron picture, one would just obtain metals. So therefore, they found some these states correlated insulating states. And they also found that when you dope away from these correlated insulating states, there is superconductivity. In the original set of papers, the TC for superconductivity was fairly low. It was around 1 Kelvin, but since then, a large number of experimental works have come up, and the TC has really improved. So right now, it's around 5 Kelvin, which doesn't seem that high if you just look at the absolute numbers. But recall that the Fermi energy is also very small of the MeV scale, so it's a significant fraction of the Fermi energy. So this phase diagram has continued to evolve since then. This is work by Efetov's group, and there they have shown that other than these correlated insulators at ±2, there are also correlated insulating states at +3, +1, depending on how lovingly you look at it. And there are indications of formation of correlated insulating states, in fact, at all integer fillings. And then in between these insulating states, on doping away, there are evidences of superconductivity. All right, so with this information, we can easily ask 2 very basic questions. The first one is, what is the nature of these correlated insulators? Are these symmetry broken states? Do they have some topological character to them? And also, what is the nature of superconductivity? What's the pairing symmetry? And what's the mechanism which gives rise to superconductivity? Is it just phonons, or is it something else? So a huge amount of work has been done to address all of these questions, and I cannot possibly refer to all of them, so please pardon any lack of reference. But in this talk, I will try to select a subset of these questions. So I will offer a possible answer to these questions of correlated insulating states at even integer fillings. And then I will back up my claims by DMRG numerics on a related simplified model, which keeps the band topology and symmetries, but kind of gets rid of the additional complication which arises due to very large unit cells. Okay, so any questions till this point? This was like a very high-level overview of magic angle graphene.
So if you have questions, please raise your hand, and I will take up those questions one by one to Shubhayu. If you have questions.
All right. So please feel free to ask questions.
Unmesh has a question. Unmesh, go ahead.
Yeah, so the explanation that you sort of gave for the flat band is through a effective magnetic field originating. Can you explain a bit about that?
Unfortunately, I myself don't have very good intuition for this. So I can say a couple more sentences about it, but I'm not sure if it will clarify too much. So what you can do is you can ask, let's take the Hamiltonian for monolayer and ask the question of what the interlayer tunneling pattern, the Moire potential due to the interlayer tunneling looks like on this monolayer graphene band. And if you write that down, it essentially looks like you add an effective magnetic field. And you know, when you add effective magnetic fields to free electrons, you get flat Landau levels. So that's my big explanation to this. But I don't have any good intuition for why this magnetic field, for example, shows up only at the magic angle.
Yeah, it's okay. I mean, this question is anyway very vague to even. I asked even this question to McDonald even, so he also like doesn't have
Yeah,
a
I
very
think.
good idea. So it's okay. Yeah.
Yeah, I think there is another way of approaching the problem, which I will discuss and which might be somewhat easier to think of. But let's wait.
Yeah.
Okay, so here is an outline of the rest of my talk. So first, I'm going to discuss this Landau level picture of magic angle graphene, which is looking at a different approximation, which may turn out to be very fruitful. And within that approximation, I will discuss charged excitations and pairing of these charged excitations. Finally, I will discuss some DMRG evidence of superconductivity from a similar model, which does not, of course, have all the complications of magic angle graphene, but retains the basic symmetry and topology aspects, and then go on to some conclusions and outlook. So let's start with the Landau level picture of magic angle graphene. So in general, when one approaches problems in correlated electron systems, there are two very prominent examples. One of them is the Hubbard model, where you start with localized Wannier orbitals, and then you add hoppings and between these orbitals and interactions on top of them. This approach has been proved fairly fruitful for the cuprate high TC superconductors. But there is also an alternate approach, which is from a quantum Hall perspective, so where you deal with Landau levels. One also sees correlated states there, but one cannot construct Wannier orbitals which are localized in both directions in space in a 2D system, for example. So one cannot construct fully localized Wannier orbitals. And in this problem of magic angle graphene, there is a particular limit called the chiral limit, which actually lends this problem to such a treatment. So recall that we had this tunneling between the layers, which takes this matrix form. So there are A and B sublattices within one layer, and then A and B sublattices in the other layer. Let's say layer 1 and layer 2, and there is tunneling between the same sublattice, so from A to A or B to B, with a tunneling strength indicated by W naught. And then there is also tunneling between opposite sublattices, which is from B in one layer to A in the other layer, say, with tunneling strength indicated by W1. So it has been found in the experiments and also in DMFT numerics, that this W naught by W1 actually goes down due to lattice relaxation effects. And the reason for this is that bilayer graphene naturally wants to be Bernal stacked, where it has A and B sublattices in the two different layers on top of each other, and that is the energetically favorable. So even if you put these two layers at a small angle of theta, then there is some lattice relaxation and contraction which enlarges these AB regions relative to the AA or the BB regions. All right, so in this spirit, let's just make kind of a drastic approximation by taking this W naught to 0. In reality, it's W naught over W1 is around 0.7, but let's just see what comes out if we make this approximation. So this is the so-called chiral limit, where we have turned off the same sublattice hopping in between layers. And as a result, there is only hopping between different sublattices within the same layer as well as in between two different layers. And this leads to the additional chiral symmetry, and it was pointed out in this beautiful paper by Tarnopolsky et al. And previously also discussed in Jose et al. And Liu et al. That this chiral symmetry allows for a sublattice and valley polarized basis, and further that in this particular basis, each band behaves like a lowest Landau level with Chern number plus or minus 1. So in this basis, which I will again, as I said, label by sublattice A or B and valley K or K prime, at the magic angle in the chiral limit, one gets exactly flat bands. Each band has a Chern number, and the Chern number between different valleys or different sublattices can be related by symmetries. So for example, Ka and K prime B, which are related by C2 symmetry, have the same Chern number, whereas Ka and K prime A or Ka and Kb, which have some form of time reversal relating them, have opposite Chern numbers. So one can think of these as bands which are perfectly flat, but under facing opposite magnetic fields. So lowest Landau levels, but in opposite magnetic fields. Of course, there is the additional spin degree of freedom, which I will suppress from now on and won't be super important, but I will make a few comments on it near the end of my talk. Okay, so now that we have exactly flat Chern bands, and each band behaves like a lowest Landau level, but then different bands see different opposite effective magnetic fields, one can ask, what's the effect of interactions on top of this? So, the physics of a spinful Landau level is fairly well understood. There, because of Coulomb interaction effects, one naturally polarizes the spinful Landau level at half filling to one spin species. And this can be up or down, in which case it will be sublattice polarized, or it can also point along the equator of the Bloch sphere, in which case there will be some hybridization between different valleys, and I will call such a state an inter-valley coherent state. So there is an interaction-driven ferromagnet in each Chern sector or layer, and this is also expected from the regular Stoner criteria for ferromagnets. If you have a flat band with formally has an infinite density of states, then even small interactions will completely serve to polarize it to a ferromagnet. So at the level we neglect tunneling between these flat bands, we have a ferromagnet denoted by a vector in the Bloch sphere, which I call n plus in one Chern sector. Let's say the C equals +1 Chern sector, and another ferromagnet in the other layer, in the other Chern sector, with some expectation value for n minus. So now we can ask what the effect of putting a dispersion back on is. So recall that dispersion hops between the same valley, but between opposite sublattices. So if I fill the same quote unquote isospin species in the two different bands, so let's say I fill Ka and K prime A, then I cannot hop because this hopping is Pauli blocked. But if I fill, let's say, Ka and Kb, then I can hop using the dispersion term because this is no longer Pauli blocked, and I can gain some energy by hopping to the other band and hopping back. So this is very much similar in spirit to the Anderson super exchange, except that Anderson super exchange worked between Wannier orbitals in real space, and here the entire story is happening in momentum space. But regardless, this dispersion term actually just conserves momenta. So you can essentially think of a momentum eigenstate where I hop from one valley, one Chern sector to the other Chern sector, and then come back. And that gives an energy gain of the order of h square over u, where u is the typical Coulomb or interaction scale. So as with Anderson super exchange, then this hopping induces a term of the form n plus dot n minus with a strength j, which is h square over u, or of that order. And this basically favors antiferromagnetism between the two Chern sectors. So let me repeat myself. In each Chern sector, we had a ferromagnet Whereas in between Chern sectors, because of this hopping term, we induce some antiferromagnetism. Also, there are further interaction terms which do not exactly obey this symmetry once we go away from the chiral limit. And while I won't discuss them in too much detail, it turns out that these favor an easy plane antiferromagnet rather than an easy axis one. So instead of the spins pointing up and down in the two different Bloch spheres, they will point in opposite directions, but along the equator of the Bloch sphere. And this is what we call the Kramer's intervalley coherent state. Intervalley coherent because, as I already discussed, this non-trivially hybridizes K and K prime. So it's contains some intervalley coherence. And also Kramer's because it turns out that although the state actually breaks time reversal, there is time reversal multiplied by a Varys rotation, which is an anti-unitary symmetry that is preserved by this state. So at this point, let me just go over the full picture again, schematically. So we started with the magic angle graphene flat bands in the two valleys, and we chose a particular way of decomposing them. So in the chiral limit, we can go to a basis which is both sublattice and valley polarized. And in this basis, we have some Chern number. And we reorganized our bands so that we have one Chern sector with Chern number +1, the other Chern sector with Chern number -1. And we formed a pseudo spin or isospin in each Chern sector. Now, because of interaction effects, one naturally gets a ferromagnet in each Chern sector. And then the question is, what if there is any relative orientation of this ferromagnet in between? And that is given by dispersion. So once you introduce dispersion back into this picture, there is some antiferromagnetic super exchange in between the layers, which ultimately favors n plus equals minus n minus. So it's a ferromagnet in each Chern sector, antiferromagnet between Chern sectors. And finally, I just mentioned but didn't explain that because of other anisotropy effects, this ferromagnet is actually, this antiferromagnet is actually an easy plane antiferromagnet, which is the Kramer's IVZ state. So this is mostly based on analytical arguments, but we also did some large-scale Hartree-Fock, keeping multiple bands, varying screening and things like dielectric constant. And it seemed like this state was fairly robust over a large region of these varying parameters.
So Shubhayu, I had one question, which is that you are thinking of a super exchange which is induced by the dispersion. But isn't there, if I take the full Coulomb and not some local Hubbard type interaction, isn't there a possibility I could have also got an exchange between these sectors through the Coulomb? Like the standard exchange mechanisms? Yeah.
Yeah, so if you take the Coulomb and decompose it, so I agree that part of the Coulomb will give you an exchange. It actually happens between the same valleys. So I need to think of why in this case you can rule this out. It's a good question. I don't know the answer off the top of my head. Need to think about it.
Yeah, and Unmesh had a question. Unmesh, go ahead.
So what is this easy plane antiferromagnetic?
It just means that this n plus will point along the equator of the Bloch sphere. So let's say it points along plus x in this direction, and n minus will point along minus x. So it has U1 symmetry. It does not break the, it breaks the U1 symmetry of rotation about the z-axis of the Bloch sphere, but it can take any orientation within that plane, in the xy plane.
Okay.
So that's why it's easy plane as opposed to easy axis, where it would point in n plus and n minus direction. All right.
Okay. Yeah, go ahead, please. Yeah.
Right. So moving on. So now we can discuss charged excitations and pairing. So in addition to particle hole excitations, which are the natural charged excitations to think about when one has an insulator, because of the Chern character of these filled bands, one can also have topological textures which carry some charge. So in particular, skyrmions in each layer or each Chern sector. So I will interchangeably use here layer and Chern sector, but please remember that it's not the layer of the original twisted bilayer graphene. But it's just easy to call it layer instead of calling it Chern sector each time. So the skyrmions in each layer will carry some charge, and this was pointed out in the seminal works by Sondhi et al. And Hoon et al. And in particular, they found that the physical charge carried by the skyrmion is equal to the product of the Chern number multiplied by the topological winding number of this skyrmion. So of course, these skyrmions can carry charge, but they can still cost a lot of energy, in which case one will not see them. So it's essential to consider the question of energetics here. So let's first discuss, following these papers, what the energetics of a single skyrmion looks like. So a single skyrmion is a texture. Because of the texture, it pays some elastic energy cost because it deforms from the original uniform orientation of the spin. But in addition, it also pays some fairly large exchange energy because now the spins in one layer are not aligned with that of the other layer or Chern sector. And it pays some Coulomb energy cost, which depends on how large it is. So the exchange energy wants to make this skyrmion small, the Coulomb wants to make it large, and this subdominant contributions from these two energetics ultimately determine how large this skyrmion is. So in the lowest Landau level for quantum Hall systems, it's found that it's indeed the lowest energy charge excitation. But once one goes to higher Landau levels, this is no longer the case. So now, instead of one skyrmion, let us consider two skyrmions, or rather one skyrmion in one layer and another anti-skyrmion in the other layer. So an anti-skyrmion is just obtained by flipping the texture from n to minus n. So because the physical charge is equal to the product of the Chern number and the topological winding number, these two layers have opposite Chern numbers and opposite winding numbers. So they carry the same charge. So naturally, one would expect these objects to repel. But in this case, they have a very nice way of avoiding paying any exchange energy cost by making perfect antiferromagnetism, or by preserving perfect antiferromagnetism in between the layers. And at the same time, they can also avoid the Coulomb cost by just becoming very fat. So they just spread over very large sizes, then they don't have to pay any Coulomb penalty. And at the same time, they can perfectly be locally antiferromagnetically aligned, and then they don't have to pay any exchange energy. So it seems that therefore these two positive charges, even though they naturally repel because of this antiferromagnetic interaction, can bind and form the lowest energy charge excitation. And while charge 2e skyrmions have been previously discussed in this paper by Grover and Senthil, and recent numerical work has been done by Wang et al. On this model, they didn't really discuss how it avoids Coulomb interactions, and also the numerical work did not contain Coulomb, but we see here that there is a very natural way for a skyrmion pair to form by avoiding Coulomb, and therefore this gives rise to an all-electronic pairing mechanisms which does not involve phonons or retardations or Goldstone modes, which are the usual culprits that lead to superconductivity. All right, so now we do have pairing, but that is not sufficient. These pairs also need to disperse or have some kinetic energy in order to have some phase coherence and give rise to superconductivity. So for example, in the lowest Landau level scenario, we do have chargey textures, skyrmions, which carry some charge, but their kinetic energy is just quenched by the magnetic field. And they don't do much interesting other than contributing to the spin susceptibility. But in this case, the charge 2e skyrmion with charge E in each layer does not see any net magnetic field, because recall that these layers see opposite magnetic fields and the charges are the same in each layer. So it can naturally be expected to be mobile. And of course, the entire dispersion here comes from interactions because the dispersion of the charge E object is completely quenched by virtue of being in the lowest Landau level. So one very cartoonish way to understand what this dispersion is, or how the effective mass arises, is as follows. So let's consider a couple of skyrmions which are moving parallelly with some center of mass speed v, and they have some distance d between them. So because they see opposite magnetic fields, there is a Lorentz force which is trying to pull them apart, which is given by their charge, which is E times phi times the effective field. But they're also attracted by this local antiferromagnetism, which is the spring force. And if we balance these two forces, then the total energy is equal to whatever the equilibrium energy was, plus the spring energy, but the distance is related to the velocity. So we can replace d by just solving this equation of qvb equals hjt. And therefore, we get a term which is proportional to v squared, and we can read off the effective mass from this. And we can see that the effective mass goes as 1 over j, and therefore Tc for a BEC of these skyrmions, which is proportional to 1 over this pair effective mass, is proportional to j. And we did compute within our models what J is for magic angle graphene, and it turns out to be of the order of 1 Kelvin. So we do get the right order of magnitude of Tc in magic angle graphene by this mechanism. So of course, this is a very cartoon picture, and we also did some more complicated field theory calculations to justify it, and it gave exactly the same answer. But for interest of time, and also because it's not so simple to intuitively understand, at least for me, I won't discuss it in more detail. Rather, I would come to the more important question of whether after adding in realistic anisotropies or Coulomb energy, are skyrmions at all energetically relevant to magic angle graphene? So for this, the first thing we need is that the stiffness should be small. If the stiffness energy is large, then we are kind of screwed anyway, because then the skyrmion energy will be larger than the particle hole gap. So here, what we have plotted 8 pi rho, which is the energy cost of the 2e skyrmion divided by the particle hole gap. And we have done it for two different values of W0 over W1, which recall are the same sublattice versus the different sublattice tunneling. So in the limit where W0 over W1 is small, this ratio is approximately equal to 0.5, which is the same as what one sees for IQH states, because in this regime, the band structure looks more or less like a Landau level. Okay, so that is true in this chiral limit. What about the more realistic limit where W0 over W1 is like 0.7? So there it's close to 1, but near the magic angle, it's still around 0.8-ish. So we do have some hope that these skyrmions are actually the energetically relevant or lowest energy charged excitations. So that, but then we also need to add other contributions due to interactions, Coulomb energy and anisotropy. Recall that there is an easy plane anisotropy, and therefore this skyrmion cannot be of infinite size. It's actually of finite size, and its size is actually determined by the anisotropy, which is not super small in magic angle graphene. So when we add all these energies, at least classically, what we find is that from the band structure computed from Hartree-Fock numerics, there is a very small pocket near the center of the mini Brillouin zone where one does get particle hole like excitations as the lowest charge excitations. But once one goes away from that pocket, then the 2e skyrmions are indeed the lowest energy charged excitations. So note that this is kind of an overestimate of the energy of these 2e skyrmions, because we still haven't really considered dispersion. So if dispersion can give rise to a band minima for these skyrmions, that can actually lower their energy. So in the rest of the talk, I will kind of assume that they are indeed relevant lowest energy excitations and try to discuss some physics of this. So if we do that, if we do assume that skyrmions are relevant, then we can try to get an idea of a rough phase diagram. So for that, we need the so-called CP1 formulation, where one writes this vector n, which is this antiferromagnetic vector, in terms of complex spinors z. So one writes n as z dagger eta z, and eta here are just regular Pauli matrices. And doing this naturally introduces a redundancy in the description because there is a phase which is arbitrary for the spinor z. And taking that into account introduces a gauge field to which this z must couple. So in this picture, the charge density is proportional to the curl of this emergent gauge field. And now we can ask what happens if we go along different directions in this phase diagram. So either by tuning doping or by tuning interactions. So first, let's discuss the insulating phase at, let's say, 0 doping and 0 interaction. So in this case, the Z's are condensed, which means that the vortices in mu, which are the charges, are disallowed. And this is the insulating phase. So there are no charges or currents at low energy in this phase. And then what happens is once one decreases the interaction effects, these vortices which were gapped, or these skyrmions which were gapped, can now condense. And that destroys this pseudo spin order or KIVC order and gives rise to a superconductor. So if one goes along the mu equals 0 line, then there is a deconfined quantum critical point where one directly goes from the KIVC to the superconducting phase. But alternately, one can also ask what happens if we dope away, which is the experimentally more relevant scenario, I guess, from the insulator. So there, recall that the chemical potential couples to the curl of A. So it actually, as one increases chemical potential, one can think of it as putting on a stronger and stronger magnetic field. And this magnetic field nucleates the vortices in N, which are 2 skyrmions. And therefore, there can be a coexistence phase where there is both KIVC insulator and a superconductor. And then finally, as one increases mu further, one expects the KIVC to go away. And then there is just the pure superconductor. So the reason why these phases can coexist is because the KIVC order in the CP1 language is Z1 star Z2. So if we proliferate vortices in Z1, but opposite vortices in Z2, which is basically this 2 skyrmion, then Z1 star Z2 does not have a vortex texture in it. So that can still be ordered while each Z field itself is not ordered. And that is the coexistence phase. If we go further in doping, then one expects that this KIVC will go away, and then both Z1 expectation value and Z1 star Z2 expectation value will be equal to 0. So one can also do like a particle hole transformation in one of the Chern sectors, and then show that this KIVC and superconductor are dual to each other, much in the similar spirit as antiferromagnetism and superconductors have been shown to be dual in some theories of high TC cuprates. All right. So this was perhaps a heavy slide and my only technical slide, so I will pause for questions.
So Shubhayu, one question, this is all in the chiral limit, or this duality statements are in the chiral limit, or do they include the other hoppings which will give you changes?
No, so this duality statement is already deviating from the chiral limit in the sense that I have already reduced myself to the antiferromagnetic manifold N. So in doing so, I have assumed that there is a fairly large antiferromagnetic coupling in between the two Chern sectors, right? So this is, of course, a field theory statement, but this is valid only when I can use a single spinor Z to describe all these phases. As soon as I have a small how should I put it? A small inter layer or inter Chern sector coupling, rather than the large one which I've assumed there, then I have to go back to n plus and n minus, and then this story cannot be told so simply. Also, the other thing which I guess I should mention is that as we go away from this chiral limit, one also includes this easy axis anisotropy, easy plane anisotropy term. But our story does go through even if one has this easy plane anisotropy. So instead of fully having skyrmions, one will have merons, but that's going to be the only kind of change in the picture. So that doesn't affect the phase diagram, but going away from the large J coupling will.
Yeah, okay. And
maybe one more comment for experts is like one can ask if within some controlled theory one can actually find this phase diagram. So we tried to do a large N theory, but we found that it was hard to reach the coexistence phase within the large N. So that gave a direct phase transition from KIPC to superconductor. So it's kind of an open question now, what controlled calculation gives all these phases. But we do know from physical arguments that such a state should exist, and it most likely exists. Of course, I didn't mention the last axis, which is the temperature. We expect both these orders to be destroyed. And there will be basically BKT transitions, since this is 2-dimension, where at 0 temperature, there is long-range order. At finite temperature, less than T BKT, there is quasi-long-range order, and then it goes away once we cross the BKT transition temperature.
Okay.
All right. So that was the theory of skyrmion pairing superconductivity with a lot of arguments and hand waving. And at this point, Velociraptor comes in and asks us if this at all has anything to do with real life, or is it just some fantasy land we theorists are living in. So in order to check that, we decided to do some DMRG, or density matrix normalization group study. But of course, doing DMRG on the full model is difficult, but we try to isolate the essential ingredients which led to superconductivity in this model. So the first ingredient is that we have spinful, nearly flat Chern bands, which have opposite Chern number ±1. So they are like flat Landau levels in opposite magnetic field, lowest Landau levels. And there is also an antiferromagnetic interaction between the Chern sectors, in addition to Coulomb repulsion. So, and there is this Kramer's symmetry, which relates Kramer's time reversal like symmetry, which relates the opposite Chern sectors. Okay, so in order to test this, we can take two spinful lowest Landau levels and antiferromagnetically couple them. So DMRG has been shown to describe several features of an integer and fractional quantum Hall states following works by Zalatel and Frank Polman and Roger Mong. And so this problem was indeed amenable to DMRG, except that we needed to figure out a clever way of putting opposite magnetic fields on the different Landau levels. So that could be done by tweaking already pre-existing code from Mike Zalatel. And therefore, we did IDMRG for this coupled Landau level model on a cylinder with Ly going from 8 to 12 magnetic lengths. So this is our Hamiltonian. So there is the free electron part, which is P plus EA, with gamma being the layer index. So it's opposite magnetic fields in the different layers denoted by gamma Z. Then we add on the Coulomb repulsion term, which is VC. And finally, there is also an antiferromagnetic interaction, which we call Ji. We have extracted a factor of Coulomb energy and LB squared to just make this dimensionless. So everything is relative to the Coulomb scale here. And we also can do the general case where we have this easy plane anisotropy. So we can take Jx equals Jy equals J plus lambda and Jz equals J minus lambda. So this is the model that we study projected to the lowest Landau level. And we can find the phase diagram at doping 2 + 1/4. And indeed, we find that beyond a certain critical J, which is smaller for small anisotropy, there is superconductivity. And outside that, there is some antiferromagnetism, even at finite doping. And also, there is some competition between the superconducting phase and a charge density wave phase. So this charge density wave here coexists with antiferromagnetism. And once we get rid of these, then we can get some superconductivity. So there is related work, not exactly on the superconducting aspect, but on DMRG by Kang and Wafik, and also on single valley, single spin sector DMRG on twisted bilayer graphene by Sojima and Parker. But here, I just want to remind you guys that here I am studying a much simpler model where one does not take into account all the complications imposed by very large unit cells. But we do find quasi-long range superconducting order. So in order to study or ascertain that this superconductivity is indeed due to skyrmions, we can also look at the insulating state and do segment DMRG to determine the energy of charged excitations. So what I mean by that is I take the insulating state, then I introduce within a segment of, let's say, some amount of span, an excitation which has a given charge versus spin quantum number, and then I try to minimize the energy. So this gives me the energy of the lowest charged excitations when I do it as a function of charge, spin, and other quantum numbers. And we can compute this pairing energy delta pair, which I define as 2 times the energy of 1e minus the energy of 2e charge. And we can do this both numerically within a nonlinear sigma model, which I really haven't described here, but we can write one down, and if there is interest, I can show what it is. And also within the DMRG. So we just compute this. And again, as we expect in the J lambda plane, if there is pairing at large J, and the J critical for pairing goes to 0 as lambda goes to 0. So this feature is the same both for the classical energy minimization, which is just done on a grid with a sigma model description of the ferromagnet, or layered ferromagnet with antiferromagnetism between layers. And here, this is directly done in the quantum system for via segment DMRG. And we see that although the phase boundaries are somewhat different, like at least close to small anisotropy limit, the phase boundaries look reasonably similar, and the energy scales are also very similar. And therefore, the numerics for the quantum system somehow confirms our classical expectations that in this regime, skyrmions are actually favored. Now, does this also coincide with the regime where we see superconductivity? So I'll come back to this, but it is indeed the case that this does coincide with the regime where we do see superconductivity. So for that, let's compare these two plots where there is superconductivity on the left in the doped phase diagram. And on the right, I am showing the pairing energy divided by EC in the segment DMRG on top of the insulating state. So here I could do an extrapolation in Ly to find what this energy is as Ly goes to infinity. But unfortunately for the doped system, DMRG is hard because it's gapless, and we are kind of numerically limited to how far we can push it. So we can only push it to Ly equals 10. And there the J critical, it does decrease with decreasing anisotropy, but at lambda equals 0, it's around 0.4. And that's the same in the segment DMRG as well. So I plot here the curves, the curves beyond which superconductivity or pairing is favored. And we can see that they form this V-like shape, which increases as I increase Ly. So at 9 lb, it's like this. At 10, it's around this. And at 11, it goes down further. And indeed, around 10, the J critical at lambda equals 0 does come out to be around 0.4. So, or 0.35 actually. So there is good qualitative agreement between the quantum and the classical numerics. So the critical J star of lambda, that going to 0 as lambda goes to 0, indicates that there is this collective pairing mechanism. And also the other point I would like to go back and make is that pairing is much more favorable in the easy plane case than the easy axis case. And that is actually good for magic angle graphene. And there is a very intuitive classical reason for this. And the reason is that in the easy plane case, these charges or charge 2e excitations can deform into topological equivalent Meron pairs, which are held together by elastic forces. So here I'm showing you simulations of the classical sigma model and the spin textures. So we can see from the left two panels that in the layers which I denote by plus and minus, there is perfect antiferromagnetism. However, the charge is not a single blob. It's actually separated, although both of the layers carry the same charge. So instead of thinking of this as a skyrmion, it's better to think of this as two merons, which are held together by elastic forces, and they can distance with respect to each other in order to reduce their Coulomb energy cost. However, this does not happen for the easy X case, because in this case, the charge texture and spin textures are all radially symmetric, and therefore this naturally incurs a larger Coulomb penalty. So forming a charged pair is harder in the easy axis case. Forming a charged pair is easier in the easy plane case. Although topologically, the Meron pair and the skyrmion, 2e skyrmion, are exactly equivalent to each other.
Shubhayu, Mandar has a question.
Yeah.
So Mandar, can you go ahead? Sorry, Mandar. Mandar, go ahead and ask.
Sorry, can you hear me now? My question is, in this language of the antiferromagnetic layers, what is the energy scale of a collective excitation? So if you think of a layer antiferromagnet, there will be two modes. One is optical and acoustic branches. So what is the energy scale for that?
Right. So the layered antiferromagnet, okay. So the energy scale of that is essentially determined by this J and lambda. So J essentially sets the ferromagnetic mode, which is the kind of mode which I guess you mentioned as the optical mode. So there, that has a gap which is set by J, and this is of the order of 1 MeV. And then there is also the acoustic mode, which is formally gapless, but of course it pays some energy because of stiffness. So the stiffness essentially sets the energy, and that is in this material also of the same order. So this stiffness energy is also order 1 MeV. It depends kind of on the twist angle and the dielectric constant and screening potential chosen, but that's the ballpark roughly.
Yeah, so I mean, if one has to test it, one basically uses terahertz.
Yeah, it's in that scale.
Okay, all right, thanks.
All right, so moving on, I would like to make one final point regarding this apparent discrepancy between the phase boundaries in the classical and quantum calculation. So I can substantiate this more quantitatively if there is interest, but for now I would just briefly mention, for the interest of time, that there are quantum 0-point fluctuations, which I don't take into account in the classical nonlinear sigma model, but they do exist. And one can find what the energy cost is, and that's proportional to this J term once one integrates out the ferromagnetic fluctuations and gets an effective antiferromagnetic model. And that raises the energy of the 2e skyrmions in the quantum scenario. So, and this actually we can try to match how much it raises, and we see that since in the classical case, at a fixed J, let's say the size of the 2e skyrmions is entirely determined by lambda. So at a fixed J, there is no dependence on J in the classical scenario for the 2e skyrmion energy, whereas there is some here, and that distinction is actually proportional to J. It grows linearly with J as we change J at a fixed lambda. All right. Okay, the last point again, which we wanted to understand was that whether we find the same kind of effective mass behavior, the m being proportional to 1 over j, as we discussed in our very semi-classical picture. And recall that the picture was that these two charges were sitting on top of each other, and then as we added momentum, they got slightly separated. And this Chern resolved dipole moment, which is proportional to ky, was related. Dipole moment, which was proportional to their distance, is also proportional to the momentum by balancing this magnetic field, effective magnetic field force, the Lorentz force, and the spring attraction in between them. So as we add some momenta, these charged textures slightly separate, and then they have some kinetic energy as well. So we can investigate this again in our DMRG, as we are allowed to put in some conserved momenta for the excitations we add on top of the insulating state. And indeed, it's kind of too crude because we can go only up to Ly equals 12 Lb. And we need a much more finer grid to look at what really happens at small Ly. But here I have plotted at least what the data which I found for the energy and the theoretically expected dispersion at lambda equals 0. And they kind of reasonably match at low ky. At larger ky, there are a large number of finite size effects which come in, and we don't expect them to match. And that's what we see. All right. So we can also kind of try to verify whether this picture of charges separating in the two layers as we put in some momenta, inject some momenta, is correct. By just directly plotting the charge density. And here I am showing a plot where I have the separation, or the real space x direction along this axis, and then the momenta along this axis, and the charge density along the z-axis in the two different layers. And indeed, we see that at zero density, the minimum energy charge excitation, at zero momenta, the minimum energy charge excitation is this 2e charge with charges on different layers lying exactly on top of each other. And as soon as we start to inject momenta, they try to separate, and their separation is proportional to the momenta injected. So again, the numerics for the quantum system confirms what we had expected from our semi-classical arguments. All right, so I think this brings me to more or less the end of my talk, and I'm probably also out of time, so this seems like a good point to end. So I argued for an all-electronic mechanism for superconductivity, which I think is somewhat different in the sense that it does not involve phonons or Goldstone modes. And this is attractive. This is an attractive mechanism for superconductivity in systems which exhibit tunnel-coupled Chern bands, but with opposite Chern numbers. And magic angle twisted bilayer graphene has the right physical ingredients to realize this mechanism. So it has the required band topology, coupled Chern bands with opposite Chern numbers, and also fairly low isospin stiffness, which were measured in some recent experiment in this paper by Saito et al., for example. So it's low of the order of 1 MeV. So we are hopeful that maybe this is indeed the mechanism why this happens in magic angle graphene. And also, one thing I would like to point out here is that while phonon-related mechanisms have been proposed, these phonons are also present in other moire materials like twisted double bilayer graphene, but those in recent studies have been shown not to have any superconducting behavior. So one crucial reason for that is that there is no C2 symmetry in the problem, which kind of changes the sublattice energetics, and this favors this hopping, which mediates antiferromagnetism that I discussed, whereas in this case, we do have the C2 symmetry, which keeps the A and B sublattice at the same energy. So there is this indirect evidence that the other material doesn't show, and this one does show superconductivity, although a lot of other things are similar between these materials, and therefore it might have something to do with skyrmions. Okay, so then there are several open questions at this point of time, some of which we are studying right now. So one of the most important questions, I think, is the effect of non-uniform Berry curvature. The Landau level has a uniform Berry curvature, which is nice. It allows for a lot of analytical computations, but it's also not so realistic because the real graphene subbands do have significant non-uniformity in their Berry curvature. And this can increase the stiffness, actually, as we found. Then recently, people have also found superconductivity in magic angle graphene placed on tungsten diselenide, which is an insulator, but it induces some spin-orbit coupling. So how much of this story goes through when there is spin-orbit coupling in the system is something we are working on. And then there is also the question of disorder and how disorder affects these skyrmions, both in terms of superconductivity, but also in terms of transport of charged excitations. There's the related question of this influence of fluctuating order parameter modes like this ferromagnetic and antiferromagnetic modes, which Mandar was asking about on transport. And as I know, I think some of these things are also being studied in different labs in India. So that's something we are also thinking about. All right, so with this, I think I will end my talk. Thank you very much for your attention, and please feel free to ask me any questions.
Let us thank Shubhayu first for a very nice talk on this skyrmion mechanism of superconductivity. And I'll now keep the floor open. So please, if you have a question, please raise your hand and we'll go one by one and take all the questions.
Okay. I don't really have a question, but I just wanted to say it was a very interesting talk. Thank you, Shubhayu. This is Kedar Damle.
Yeah, thanks, Kedar. I really hope to give this talk at some point in TIFR.
Yeah, it would be very nice to have you here physically, but right now this is the best we can do.
Yeah, in fact, I was actually, before all this happened, planning to travel to India sometime around this time and then go and give talks, but unfortunately.
Yeah. Once you can travel, do come to our shores, and yeah, we'll be very happy to host you. Unmesh has a question. Unmesh?
Yeah, so I have a couple of questions. One of is that you started this thing with a chiral limit with WA to be 0. Then you showed a data where you talked about also this non-chiral limit around 0.75 or so some. So what is it like? How did you also do the calculation for non-chiral limit? As far as I understood that for chiral you had this flat Chern bands and you could do this skyrmion thing, but for non-chiral thing?
So there, I guess you just have to like do the calculation numerically. So let me try to recover the slide where I discussed this. So this was, I think here, yeah. Right, so go to full screen. Right, so in this case, what we did was we just computed the gap from doing Hartree-Fock on the model of free electrons like Bits-Ritz or McDonald bands plus interactions. And there, once we had the bands numerically, we could numerically evaluate the Chern numbers. Like there is, I don't think there is a good way, at least not any that I know of, where one can approach this problem and analytically from in the non-chiral limit. Like the good thing which does happen from the chiral limit, which is why this approximation turned out to be somewhat useful, I guess, is that you start with the chiral limits and then there are perturbations. There are perturbations which come from dispersion. There are also other perturbations which come from the non-chiral, chirally symmetric part of the interaction itself. And if those two perturbations led to different kind of ground states, then we couldn't really say that this would be this easy plane antiferromagnet, but it turns out that both of these perturbations favor the same ground state. So that gives us this state as an energetically favorable state. But then If you want to really show that all of these holds away from the chiral limit, you just numerically evaluate the band structure and numerically find the Chern number.
Yeah. So let me ask this question also that
Yeah.
so you calculate this TC, right, from your numerical or theoretical A also, but did you try to match with the TC with any available experimental TC and see at which non-chiral limit this happens, or?
So the TC that we calculated, yeah, that's a good question, and we didn't calculate it exactly in the chiral limit. We did have the J term, which is the dispersion induced term, which does come about due to deviations from chirality. So because we are already putting in dispersion, where was that slide? And yeah, so recall that we do need this J to have this mechanism at all. Without that, there won't be any skyrmion pairing. But then you can ask what's also the effect of the easy axis or the easy plane anisotropy, the fact that these are really merons rather than skyrmions. And that I don't have a good answer to. Like I haven't figured out yet how to analytically have a simple picture where we can put in the anisotropy and then compute the mass. So of course in the DMRG we can do it, and that's what we did. So let me go back there. So in DMRG we can choose whatever value of J and lambda we want. Lambda was the anisotropy, and of course we chose small values of lambda so that we could keep in the regime where superconductivity is favorable, but we could also go to larger lambda. One issue with that is, if you recall, there is this kind of separation in between the charges as you increase lambda.
Yeah.
And our DMRG has a finite cylinder circumference. So once the cylinder circumference becomes small, then it doesn't really allow these charges to separate by as much. So we don't get very accurate data at large lambda, which is, I think, also the reason why we don't see superconductivity here in DMRG, whereas we do see it in the nonlinear sigma model. I shouldn't say superconductivity, I should say pairing, but yeah, it's kind of the same thing as long as you believe that this is the mechanism.
So in the real space, like what is the kind of spatial order of this like skyrmion thing? How much?
Yeah, that's an excellent question. So I know how to think of this in the sublattice polarized limit. So we go back to this band structure. Right, so we have to go back and ask what is the pseudospin, and the pseudospin, what it is doing is it's pointing in between two different sublattices, and it's also pointing in between two different valleys. So what it will do is that it will mix the two valleys, which might lead to some local currents, and it also has some kind of sublattice polarization. So let's say you start with a state which is this IVC state. Then if you go to the center of the skyrmion, then it becomes the IVC with the opposite phase. But you could also ask what happens if you go in the middle of the skyrmion, where this might point along the z direction, and there it will be sublattice polarized.
So let me just end with probably a dumb question. So this ferromagnetic or antiferromagnetic interaction and all this, this doesn't have anything to do with this 3/4 filling ferromagnetism that people see in Lucifer.
Yeah, so that's also a very good question. It does have something to do with it. It can be kind of explained by the same picture, but recall that the physics is very different once we fill 3 of these 4 bands instead of filling 2 of these 4.
Yeah.
Right. So here we could say, okay, we can fill one band in one Chern sector, another band in another Chern sector, and then we try to find, okay, among these, how should we fill this band so that the overall energy is minimized? But now at 3 out of 4 filling, you have to fill 3 of these 4 Chern bands. So then you can see that the natural way of filling it is like filling one sector fully and then filling half of the other sector. At least in the limit where you have flat bands, that will give you a fully gapped band structure with the minimum energy. But if you fill one Chern sector fully and only half of the other, then you naturally turn out to have a non-trivial Chern number. So that is this. So then also you have some kind of orbital ordering, which is this orbital ferromagnetism. But in addition, you have net Chern number, which is why you see a quantized Hall effect in this at 3/4 filling. Like, one question is, why don't you see it at 1/4 filling? So some people have seen it at 1/4 filling when you turn on a small field. So maybe there are some competing states which are becoming more favorable due to disordered effects. That might be the case. The other question is, why don't you see any of this at -1 and -3 filling? You would also see that you should also in principle see the same physics, but there it has been hard to obtain insulators. So although this problem, at least theoretically, the way we studied it, has some approximate particle hole symmetry, I think that the real system doesn't really have a good particle hole symmetry, at least the samples which have been studied till now. Maybe in the future, better samples will come up, which closely resembles our
nice talk. Thanks a lot. Yeah.
Thank you. Thanks for the questions.
Any other questions from anybody else? If not, let's please unmute and thank Shubhayu for this very nice talk that he gave us.
So Rajdeep, like regarding your question about exchange, one also needs to consider additional effects of form factors, which are these block overlaps between the bands. I think once you consider that, then this ferromagnetism goes away, if I recall right. But I will look into it and send you a more detailed answer later. But I just recall that these complicated form factors turn out to play a very significant role in what the ground state is. I neglected all of that in this very simplified picture, but they are there and need to be taken into account more carefully.
I see.
Okay. Thanks, Shubhayu. So that we will